So welcome to the lecture on state space method. So in this lecture we will continue with one example, the conversion from transfer function to state space, as well as we will discuss also how to convert from state space to transfer function. So we were discussing that when we have a transfer function, we first convert this transfer function to a differential equation by taking the inverse Laplace transform, and then we select the state variable as phase variables. So we select one state variable, the output, and then the next state variables will be the derivatives of the variables called phase variables. So we can write the state equation and output equation for a transfer function. Now we take one case when we have the numerator, there is a transfer function in the numerator as well. So how to deal? So if we have this case, so we have here this is the numerator of the transfer function, and this is so earlier we only deal with, there was no any function on the numerator, but it was taken with some constant parameter, but now it is function of s. So when we have a transfer function has a polynomial in numerator that is of order less than the denominator, we can separate into two parts. So if this is our output CS and this is RS, so we can write this like, we can separate it. So first we can write as only denominator part, and the output of this part could be input to the other part, that is the numerator part, b2 s square plus b1 s plus b0. Let's say this is x1 s and this is rs. And let's say internal variable here is x2s and x3s, and x1s is the output of this part. So here ys equal to cs, that is equal to b2 s square plus b1 s plus b0 into x1 s, and we take the Laplace transform with initial conditions 0 of this, we will get b2 into d square x1 by dt square plus b1 dx1 by dt plus b0 x1. So here we know that we can write, because this, if we have x1 as state variable we have selected, so x2 equal to dx1 by dt, the next state variable, and x3 equal to dx2 by dt, that is d square x1 by dt square. So we can write here as b2 into x3 plus b1 into x2 plus b0 into x1. So we can represent this output in terms of the state variables that we already defined in this first part. So let's take one example. So we can see that the final output, so this is CS or so we here this is equal to CT, we can say also. So we see that here this is only collecting the state variables that were already defined in this first part. So here b2 x3 plus b1 x2 plus b0 x1. So now let's take one example. So we have an example. So we have s square plus 7s plus 2 upon s cube plus 9s square plus 26s plus 24. So this is the transfer function having some numerator, polynomial in the numerator. So we can represent this as Rs one upon s cube plus 9 s square plus 26s plus 24. And this is x1 s, and there is second block, that is s square plus 7s plus 2, and this is CS. Now we know that this part we have already learned how to write the state equation. So if we have x1, x2 and x3, the state variables, where x1 equal to the output of this and x2 equal to x1 dot and x3 equal to x2 dot, and that is equal to x1 double dot. So we can write this as x1 dot, x2 dot and x3 dot. These are the state equations we are writing. So we had earlier we solved for the same system, except here was 24 and this 24 was coming here to the input. But here now we have input R and 0, 0 and 1, because now here is 1, so we will have here 1. And we know that here we have x1 dot equal to x2, so 0, 1, 0, and x2 dot equal to x3, so 0, 0, 1, and this last row is, these elements are reversed with negative sign, so minus 24, minus 26 and minus 9. So this is the state space form for this part. Now we can write x1, this CS equal to s square plus 7s plus 2 into x1 s and therefore we can write Ct equal to here x1 double dot, because we take the inverse Laplace transform, plus 7 x1 dot plus 2 x1. So here x1 double dot is equal to x3 plus 7 x1 dot is x2 plus 2x1. So we are representing in terms of state variable. So we can write this is y equal to Ct. So output. So this is the output equation. We can write y equal to x1, x2, x3. So 2, 7 and 1. So y equal to 2, 7, 1. So we can see that this block, this simply collected these variables to give the output y. So in output we have 2, 7, 1, this matrix. So that is how we will go for writing the state space equations for a transfer function having polynomial in numerator of less order than the denominator. So now we will discuss how to convert from state space to a transfer function. So we have to discuss how to convert, how to get the transfer function if we have the state space form. So if we have this equation x dot equal to ax plus bu and y equal to cx plus du. So if we have these two equations, so we have the state space form and we have to convert it into the transfer function. So we take the Laplace transform. We take the Laplace transform. So this is x dot. So we will have s xs. So one derivative. So we get s plus. So equal to a into xs plus b into us. Now ys, we take the Laplace transform of this. So ys equal to c into xs plus d into us. So we solve for xs. So we find xs. So when we want to solve for xs, so si minus a xs. So we take this side. So si minus a equal to bus. So from here we can get xs equal to, so this is a matrix. So we will get si minus a inverse into b into us. Now ys equal to c xs plus dus. So here c into xs, we have this si minus a inverse into b into US plus D into US. So we can write here this as C into Si minus A inverse B plus D US So what is this? So here U was the input. So here U was the input. So US is the input, and Y was the output. So YS is the output. And so what we are getting here, if we say GS. So here this is, we can write YS equal to GS into US. So or YS by US equal to GS, and this GS equal to this quantity, that is C Si minus A inverse B plus D. So this is the transfer function. So we remember that these are the matrices. So now we can take one example, and we can show how for a given state space we can write the transfer function. So we have this equation x dot equal to so this is the, we can see the, this is the state equation, and this is the output equation. So we are given the state space model for a system. Now we have to find the transfer function for this system. So to find the transfer function, we can find GS equal to C Si minus A inverse B plus D. So this is the transfer function. So first let's calculate Si minus A. So Si minus A equal to, so here the matrix A equal to 0 1 0 0 0 1 and minus 1 2 3, because we can compare this with x dot equal to Ax plus Bu, and output equation we can compare with y equal to Cx plus Du. So when we do this, we get that A is this matrix and B matrix equal to 10 0 0, and the C matrix here Cx, so C matrix equal to 1 0 0, and D matrix is null. So we find Si minus A. So S here S 0 0 0 S 0 0 0 S. So this is Si, because we multiply S in the unity matrix I matrix. So this minus A, so A is 0 1 0 0 0 1 and minus 1 2 3. So we will get Si minus A equal to S minus 1 0 0 S minus 1 1 plus 1, so 0 minus minus 1, 0 minus, so minus 2, and S minus 3. So here this is minus 2 and minus 3. So we have minus 2 minus 3. So here this is 2 and this is S plus 3. So there is a correction. So now we find Si minus A inverse. So to find the inverse, we can find adjoint Si minus A by determinant Si minus A. So we can find this. So this is the numerator part. Then denominator, it is S cube plus 3S square plus 2S plus 1. Now we can get the transfer function from here. So we have GS equal to C is 1 0 0, and we got Si minus A inverse, and B is 10 0 0 plus D we can have 0 0. So from here we will get here we have obtained from the state equation, given state equation, we have obtained using this relationship. First we calculated, we identified the matrix A, B, C and D. Then we calculated the Si minus A, then we calculated the inverse. So adjoint Si minus A by determinant Si minus A, and then we put these matrices. So I think here it should be 0. So we will obtain this transfer function. So we learned today about in this lecture about how to convert from state space to a transfer function and from transfer function to a state space. So I stop here and we will continue in the next lecture. Thank you.